Have you ever really stopped to wonder what makes one computer faster than another? And I don't mean the brand name or the cool glowing lights. We're going to go deep, deep inside the machine to understand the basic principles that make our entire digital world work. And it all starts with a simple question that, it turns out, has a really complex answer.
So it all kicks off with this puzzle, right? You see two computers. Both say they have an x80-64 processor. The same family of chips from Intel or AMD. But one is this absolute beast of a gaming machine, and the other is a super basic budget laptop. How is that even possible if they're supposedly built around the same thing? Well, that's the big mystery we're going to solve today.
And here's our game plan to get us there. First, we're going to break down the difference between architecture and organization. Then we'll cover what a computer actually does. After that, a quick history lesson, from room-sized computers to tiny chips. We'll look at the one law that drove all of that progress. And finally, we'll see how this all applies to the processors in your pocket right now.
All right, Section 1, architecture versus organization. The absolute best way to think about this is like a building. You've got the architect's blueprint, and then you've got the actual construction crew that builds the thing. One is the plan, and the other is how you make that plan a reality.
So, computer architecture? That's the blueprint. It's the official set of rules. It tells you things like what commands the processor understands. That's the instruction set. Or how it talks to all the other parts of the computer. The most important phrase here is visible to the programmer. This is the contract, the promise. It guarantees that if you write software for this architecture, it's going to work. Period.
But computer organization, now that's the build. It's all about how you actually deliver on that promise. This is where the magic happens, or doesn't. We're talking about the nitty-gritty hardware details that are totally hidden from the programmer. Things like how big the super-fast cache memory is, or what kind of memory technology they used. The programmer doesn't need to know how it's done, they just care that it gets done. Let's just put it all side by side to make it crystal clear. Architecture is the what. Organization is the how. Architecture ensures your software will run. Organization determines how fast it runs. And here's the key that unlocks our whole mystery. You can have tons of different, clever, and unique organizations, all executing the exact same architectural blueprint.
This quote just nails it. Architecture is the public promise. Organization is the secret sauce, the hidden engineering that makes one computer a snail and another a rocket ship. And this is why two x86-64 machines can be so incredibly different. They have the same contract, but a totally different implementation.
Okay, so now that we've got the what versus the how sorted out, let's peel back another layer. What does any computer, from a giant supercomputer to the little chip in your toaster, actually do? It really just boils down to 4 basic things. First, it processes data. That's the number crunching. Second, it stores data. It's got to remember stuff, right? Both for a second and for years. Third, it moves data. It has to get info in and out, from your mouse or from across the world. And finally, control. Something has to be the conductor of the orchestra, making sure everything works together in harmony. And not surprisingly, those 4 jobs are handled by 4 main parts. You've got the CPU, the brain, doing the processing and controlling. You've got main memory for short-term storage, I/O, or input-output, for moving data around, and finally, the system interconnection, which is like the nervous system or the highway that connects all the pieces so they can talk to each other. Now, the way we've organized these parts has changed a lot. It's been this incredible shrinking journey, which is really just the story of getting better and better at computer organization. The first generation of computers use these massive, hot, unreliable things called vacuum tubes. We're talking computers that filled entire rooms. Then came the transistor, a total game changer. It made computers way smaller, cheaper, and much more reliable. But the real revolution was the third generation, with the invention of the integrated circuit. The idea that you could pack a bunch of transistors onto one tiny sliver of silicon, that changed everything.
And just look at the explosion in performance. A first-gen machine chugged along at 40,000 operations per second. Transistors boosted that to 200,000. And with integrated circuits, we hit 1,000,000 operations per second. This was an absolutely insane rate of improvement, and believe it or not, things were only just getting started.
So what was the engine driving this incredible exponential progress? Well, it can pretty much be summed up by 2 words that define the entire tech industry for 50 years. Moore's Law. Back in 1965, a co-founder of Intel named Gordon Moore just noticed something. He saw that the number of transistors engineers could fit onto a single chip was basically doubling every single year.
Later, that pace slowed down a bit to every 18 to 24 months, but that simple observation became a self-fulfilling prophecy for the whole industry. It became the target everyone aimed for.
So why does this matter so much to us? Well, when you can pack more transistors on a chip, the cost for each one plummets. And as things get smaller, the distance electricity has to travel gets shorter, so speeds go way up. Computers get smaller, they use less power, and they get way more reliable because there are fewer separate pieces to wire together. This is literally why the phone in your pocket is more powerful than a supercomputer that used to fill a room. Let's just try to put this into perspective for a second. The very first microprocessor in 1971 had about 2,300 transistors. Fast forward to 2013, and a single Intel Core i7 chip had 1.86 billion of them. The scale of that growth is it's almost impossible to really wrap your head around it. And it was all driven by the relentless pace of Moore's Law. All right, so let's bring it all back to today. How do these big ideas of architecture and organization play out in the gadgets we use every single day? Well, right now, it's mostly a tale of two different architectures, x86 and ARM. On one side, you've got x86 from Intel and AMD. It's what's called a complex instruction set. Think of it as being built for raw, maximum power. It's the king of desktops and servers. On the other side is ARM. It's a reduced instruction set. Its whole philosophy is about simplicity and incredible power efficiency. And that's exactly why it completely runs the world of mobile phones and other portable devices. Two different blueprints for two totally different jobs. And here's the wild part. The most widely used processor architecture on the entire planet is ARM. Why? Because of something called embedded systems. An embedded system is basically a tiny computer with one specific job inside a bigger device. And they are everywhere, in your phone, your car, your microwave, your TV. We're talking billions and billions of them. And they all need a cheap, efficient processor that just sips power. That's ARM's sweet spot. So let's bring it all home. If you remember one thing from all of this, let it be this. Architecture is the timeless blueprint, it's the what. It rarely changes. Organization is the constantly improving, mind-blowing technology that brings that blueprint to life. It's the how. It's what makes our devices faster, smaller, and better every single year. And that leaves us staring at a massive, fascinating question for the future. We're hitting the physical limits of Moore's Law. You can only make transistors so small. So the next giant leap in computer speed isn't going to come from just shrinking things anymore. It has to come from brand new, maybe even radical ideas in computer organization. What will that be? Well, that's the billion-dollar question for the next generation of engineers to figure out.